AMD's new EPYC CPUs are launching today, codenamed Turin, but they're based around Zen5. Zen5 already launched on the desktop, but really, except maybe the part where they added the Zen5 cores, there's much more important going on in this platform that overshadows the core itself that I have to talk about, because it's a lot. A lot of my wishes are finally come true, and I'm in my happy place. Well, it's complicated because, competition and everything else going on in the market. We've got a lot of information to get through, and well, let me explain melodically before the bump. To every workload, Turin, there's a feature, Turin. A time for more threads, a time for less power, a time for more throughput, a time for more cores, Turin. To every server, Turin. There is more bandwidth, Turin. There are more cores. Well, with deep apologies to the birds. I'm just having a bit of fun. Listen, I too have the attention span of a goldfish, and AMD dropped some of these details already, but let's recap and put them together because it's going to be important for the context of this review. Zen5. This is an all-new microarchitecture and greatly enhances the capabilities of the I/O die. There's a lot of net new features that we can see on AMD's slides for this generation. First off, they added full support for DDR5 6000, natively, officially supported. You can expect DDR5 6000. A lot of my benchmarks were ran with DDR5 6000. The AVX 512 pipeline is full speed, 512 bits wide, all new cutting edge reliability, availability, and serviceability. That's RAS features. And a lot of the platform hardening beyond what you'd expect from basic ECC functionality all the way through the I/O hardening to be ready for CXL memory expanders, because then the PCIe bus is going to handle memory transactions. Well, it's not really the PCIe bus, it's CXL. With these new CPUs, it will work in the Genoa socket, and the highest end CPUs are now up to 500 watts. So it's going to be up to system builders and integrators to qualify their existing designs for both DDR5 6000 and 500 watts. 2 DIMM per channel configurations also get a speed bump as well, but it's still not possible to run DDR5 6000 in a 2 DIMM per channel configuration. But you do get a little bit of a memory speed bump there. We're also looking at 6 terabytes per socket, 512 gigabyte 3D stacked DIMMs, full support from AMD. AMD also talked about enhancements to simultaneous multi-threading. I mean, okay, I didn't get what they meant. They meant a lot with that. AMD is doing something unique and interesting in the direction that they're going for 2 threads per core, and we need to talk about that because the groundwork that they've laid to feed the beast is pretty wild. First up, here's the full product stack. This is EPYC 9005. Remember, the last digit is the generation, and there's a lot in these families. There's 3 CPUs in particular that we're going to take a look at in dual socket configurations. The 9965, 192 cores. This is what's called Turin dense. They're able to do all this in just 12 CCDs, 16 cores per CCD. And AMD explains that as they've optimized the layout of the chip floor plan to optimize for power efficiency, well, that's going to reduce the real estate required per core, but that also reduces the frequency ceiling per core, but you can fit twice as many cores in basically the same area with the same shared 32 megs of L3 cache per 16 cores. This is one we're going to have to come back to because the geometry of this processor is something special. It's 500 watts, but surely a single socket server with 192 cores and simultaneous multi-threading for 384 threads couldn't go toe-to-toe with a dual socket 250 watt CPU, 144 cores from the competition. Surely. Hey, wait a minute. 12 chiplets? What, doesn't the 128 core Zen5 EPYC connect 16 chiplets for 128 cores, implying 16 core chiplets, 256? Yeah, that's going to be another video. Like and subscribe and watch out for that, and don't call me Shirley. Anyway, the 9755, this is the 128 full-fat Zen5 core with all the fixins, 256 threads, that's 16 8-core chiplets, sucking back a healthy 500 watts of power per socket. Now, if frequency's your game, say hello to my little friend, the 9575F, a 64-core, 128-thread, 400-watt monster CPU with turbos of up to 5 gigahertz. The benchmarks on this one are also quite surprising for a number of reasons. Many of you will be looking at the computational fluid dynamics benchmarks and building workstations around this CPU basically immediately, I think. And if you're Dell or Lenovo or HP and you're watching, you don't have to wait on AMD here at 5 gigahertz and up to 500 watts per socket. You know, you've got the group of engineers that have the capabilities to build the highest end workstation platform just based around those EPYC F series CPUs with some minor details like sleep figured out. I mean, servers don't sleep. This is, you know, this chip, this F series chip is the chip dreams are made of. 64 core, dual GMI links, 5 gigahertz. Every chiplet has got twice the bandwidth because of the dual GMI links. Now, in case you're fixated on that 500 watts per socket, think instead of watts per unit compute. And the benchmarks will quite clearly show that processors from just 3 years ago, we've approximately 3x'd those in performance in roughly the same power envelope. We've gone way, way, way down in watts per unit compute, and the economic sustainability thing is a consideration. With AI, at least right now, workloads are expanding at a geometric rate, and so on a macroscopic scale, yeah, things do look pretty interesting. But that's above this computer janitor's pay grade, what with bringing the nuclear reactors online. Let's just look at the numbers. Let's look at the numbers of the benchmarks and everything else, and then we'll talk turkey. Now, one of the most exciting areas of AMD Zen 5 architecture are the updates to everything that's not in Zen 5 core, like I was saying before. I mean, I'm sure, we're seeing 17 to 40% generational improvements from Zen 4, which is already kind of a monster, and that's really exciting. But you can't do all that with a core alone. And something that I've always harped on is, sure, Zen is fast, but I need to get stuff in and out of Zen for it to do me any good. And that means faster and more reliable PCIe, memory bandwidth, better utilization of memory bandwidth, memory controller. Oh boy, has AMD delivered on this generation. If anything, it's made me even more excited for Zen 6, because as good as Zen 5 is, Zen 6 is going to have a stellar foundation to start from. Well, what am I talking about? The machinery in the I/O die, sometimes, well, some of the core stuff too, that supports things like memory-to-memory transfers, bandwidth, connectivity. It's all a significant leap from the previous generation. We've used a few tools to really dig into the impact of these changes, and I found some interesting things. Multi-chase. Multi-chase is this core-to-core, CCD to CCD latency measurement tool that wasn't really on my radar before, but this one was developed by Google, and this is a little bit more real-world than the core-to-core latency checkers that we were seeing when Zen 5 Desktop launched, I think. And so this is, I think, what AMD has been using to benchmark die-to-die and core-to-core and chiplet-to-chiplet latencies, and maybe explain some of the differences that we saw on the Zen 5 launch, but have now been corrected on Zen 5 Desktop, because the core-to-core latencies here show quite good. I mean, we're on 209 nanoseconds to 212 nanoseconds, chip-to-chip latency, socket-to-socket, and inter-chip latencies of 108 nanoseconds, meaning from CCD to CCD, which is quite good. And that's important because Zen 5's architecture is designed to reduce latency between chiplets, so that faster communication within the system is a direct benefit. Transfer Bench is another one, and that one is from the ROCm team. So that's a ROCm-based utility that lets you measure data transfers between various devices like CPUs, GPUs, and memory. The real story here is how effectively data can move across different system components, and that's important when we're talking about CXL, when we're talking about building, giant AI GPU fabrics from these. We pushed transfers between GPUs and DRAM, leveraging the new architecture, and we saw improvements in both bandwidth and latency. Zen 5 is built for speed, but whether you're talking about internal transfers or external I/O, it doesn't matter. Zen 5 will just eat all that for lunch, and that's really, really exciting. One highlight, we nearly saturated a bonded to dual 400 gigabit link during RDMA transfer tests, peaking out at about 740 gigabits per second. That is a staggering result, and that was very, very difficult to achieve on Zen 4. I suspect this is partially thanks to the dual GMI 3 links on each chiplet. That's a new thing. Check out the diagram. In the higher core count CPUs, you only get the one, but for 64 cores and below, you get two. Well, there's 8 chiplets, not really by core, it's by chiplet. InfiniBand with RDMA also shows great generational performance uplift, faster transfers, lower latency, and less CPU utilization. One of the key changes AMD made here is the introduction of a virtualized interrupt controller, which applies to pass-through and virtualized workloads. This cuts down on the overhead for VMs that demand high I/O or high I/O workloads by reducing the load on the host OS by just passing through more hardware. So with heavy virtualization, that's kind of a game changer. It also means you can do things like trusted I/O. It doesn't stop there. Another massive improvement comes from the memory controller itself. Zen 5 now supports 12 channels of DDR5 6000 up from DDR5 4800. That's 25% memory bandwidth increase on paper right off the bat, but the memory dependent benchmarks that we ran actually show a 28% increase because we know Zen4 left a little bit of memory performance on the table. So server memory being faster than what is officially supported desktop memory, that's pretty remarkable. This is especially true because it's registered error correcting memory, making the server environments more robust and faster than ever. I mean, honestly, it's impressive to see that server-grade registered ECC memory at DDR5 6000 officially supported has reached this level of performance. I mean, historically, desktop memory, for what is officially supported, has always had the edge. But now AMD has this whole family of server CPUs with officially faster supported memory than desktop CPUs in general. This is, I think, the first time that's ever been true in history. Big deal. CXL plays a role here, too. CXL devices at the kind of the PCIe end of connectivity. I mean, PCIe links, but more protocol, not exactly PCIe, show a latency of about 220 nanoseconds when they're doing a memory expansion type role. That means that it is possible to add loads and loads and loads of cheap, fast memory to servers that have workloads that need lots of memory. I mean, sure, you can do 6 terabytes per socket, as is right now with your DDR5 slots, but 512 gigabytes per DIMM is about 10 times the price of 128 gigabyte DIMM, whereas a DDR4 based CXL device that uses a CXL interface is significantly cheaper just based on the component cost alone. Though I haven't really seen any of those in the field yet. They're coming. They're coming. Oh, and check this out. Here's my Liquid PCIe fabric setup in the basement. Liquid enables me to move PCIe hardware from physical host to physical host without too much headache. Each interface card here is 16 lanes of Gen 4 bandwidth, and I can use multiple cards to get multiple ranks of bandwidth out of this thing, so I can connect systems to the fabric and swap physical PCIe devices across hosts. So as part of my testing, and these Turin CPUs, I connected 4 Instinct MI210s with my standard Danny DeVito image generation suite into the new Turin system. Also did some model training for an unrelated special project you'll hear about soon enough. These jobs take a long time to run and constantly swap data in and out of the GPU and store it on blazing fast local Kioxia CM7 Gen 5 SSDs. Using these 4 GPUs, I tested both the model load time and generation time for the full workload, basically running the job until completion, run the job again, complete it, and then just time the time it takes to run through everything and all aspects of those jobs. What I found was that the Turin-based configuration with those GPUs for my specific test, again, kind of sample size of 1, but also really impressive. It's 8% faster on Turin versus EPYC Milan 7543 setups, which I just have in my, kind of daily setup with those MI210 GPUs. And that's kind of astonishing because the workload doesn't run on the CPUs. All the CPU is used for is I/O and shuffling the data around. And yet, the new platform is pretty darned impressive. If you've been following us for a while, you know that some of our intrepid heroes in the Level 1 Techs community are keeping the torch going by testing COMSOL, computational fluid dynamics software, on all manner of hardware and math library configurations. Because the math library actually matters a lot. We've got 3 different benchmark configs, well, actually more than 3, but 3 that I'll talk about today. CFD this model only uses a little bit of RAM, but it consumes lots of CPU resources. Runtime on a fast computer is about 23 minutes using only about 10 gigabytes of memory. Electromagnetics only is a model that uses quite a lot of RAM, but not really a lot of CPU resources, but that can matter if your memory controller is not up to snuff. 60 minutes using 260 gigabytes of memory. Our 9575F with 64 cores and 1.5 terabytes of memory, it's overkill. You can just pin it to a couple of cores. With these two, it's 11 minutes and 52 seconds and 7 minutes and 4 seconds with no tuning. With tuning, I can get both of those below about 5 minutes. COMSOL is one of those where the math library is also important. And it's still the case that Intel's MKL, that's the math library, results in about a 10 to 15% faster COMSOL solve time than AMD's AOCL. I mean, the AVX 512 improvements here are no doubt responsible for the significant performance improvements that we see over AMD's prior Zen 4 generation as well. But for computational fluid dynamics, this is going to have some people saying, you got COMSOL to run that how fast? Zen 5 is the real deal. It's very impressive. There's a lot of really interesting results in the overall benchmarking, not just from the Phoronix test suite, but also some of the other testing that I did. Take, for instance, OpenVINO. So OpenVINO, if you just look at the out-of-the-box performance. Okay, yeah, Turin goes toe-to-toe with the 6980p. That's really cool. OpenVINO, Intel has their AMX extensions, etc., etc. But if you do a little bit of kernel tuning and a little bit of software tuning, you can get Turin to pull ahead. And this is a really astonishing result. OpenVINO faster on Turin. Like, this is probably going to spawn a whole other set of videos and benchmarks. There's other little anomalies like that. I mean, yeah, sure. In some of these, the 6980p 128 core pulls ahead because that is what Intel is building for. And you see that in these results. But OpenVINO, this fast on Turin, you got to hand it to the AMD engineering team. This is really, really impressive. Now let's talk for a second about Turin Dense. 192 cores, but these are the compact cores. 16 cores per 32 meg cache segment and 12 CCDs a chip. Covered all that. This is the single biggest generational improvement that AMD has had maybe since Zen. I'm talking about from Bergamo, 128 cores in this socket, Zen4C to Zen5C. AMD has really undersold it. For most workloads, not absolutely every workload, but 192 Zen5 compact cores or Zen5C cores. Wow. It's something else. AMD really doesn't leave much on the table in terms of memory bandwidth, I/O performance, not much of anything else. I mean, these are really, really fast. If anything, the I/O die is maybe holding these 192 cores back just a tiny little bit. But I think they've got enough headroom here to go to 256 cores if they really wanted to, especially if the workload is going to live on most of these systems. If you've got an OpenShift type workload where you want to pack on a bunch of, small compute instances like 4, 6, 8 cores and just have a massive fleet of containers or some sort of massive orchestration, this platform, what is very difficult to convey from just looking at the benchmarks is that these are the same Zen5 cores. You really don't have to change your workload a lot. What you lose over the Zen5 counterparts is that ability to do the top-end burst, is the ability for like a bursty workload, or you have a workload where the system is not, 70% utilized or better through the whole job. You lose that. And so like if you had a bursty workload or you had something where higher single core performance made more sense for your workload, which is a lot of workloads, then yeah, okay, maybe this makes sense. But for density and even legacy migration, like if you wanted to migrate and consolidate racks of systems into, 2, 3, 4, 5 systems based around this platform, I mean, you could do it. You could do it, and it's really no compromises. You're not really trading very much at all in that sort of legacy migration scenario. And that really underscores something amazing that's happening here in the market, because Intel has basically adopted AMD's philosophy, and they have their first products out that follow that. And yeah, in the benchmarks, we do see that there are some benchmarks where Intel pulls ahead, but the AMD processors here are monstrous. They're absolutely intimidating monsters for what they are. This is a love letter to system administrators and CTOs, especially those that have been on the fence about upgrading legacy systems or older systems. This is a love letter written by AMD to those folks saying, yes, now you can upgrade. You can upgrade basically any way that you want. This will be the ideal platform for launching into an AI thing if you want, because you can host an absurd number of GPUs. You can do like I was doing, using a liquid fabric to compose those into existing servers or to existing new servers or planned servers or whatever, rather than deploying those from day one. But all of your legacy and existing workloads, no matter which way you want to go for density and power efficiency, or power efficiency and just raw performance, you have an option. And even if you have workloads that make more sense for accelerators that AMD doesn't have, things like AMX, AMD still holds its own even in those workloads where, yes, Intel will pull ahead because there have been software optimizations. But look at how much performance is potentially left on the table, even just optimizing for AMD's platform. The AES 128 benchmarks. I was scratching my head a little bit here because the Intel CPUs pulled so far ahead. But really, this is just down to choices the compiler makes and little software optimizations. Just spending 10 minutes looking at why it was running slow. It's like, oh, yeah, I could recompile this. And then all of a sudden, this platform is performing better. and it may be possible to do the same kinds of things. I did look at, trying to do a like-for-like test on the Intel platform because I also have the 6980p running a bunch of stuff in the background and trying different geometries and different kernel parameters and trying to do as much of a like-for-like comparison as I am able to do. And the Intel competition is formidable. If you're running an 8380 Platinum CPU, something from just, 2, 3, 4 generations back, it really looks pitiful. Basically everything that's more than 2 generations old is so far in the dust now that it is just, it's absurd. If you're hanging on to those old legacy systems, it no longer makes rational sense, let alone logical sense. This is a love letter to all the people that have to run these workloads and maintain these systems that, 2025 might be the time that it's time to upgrade those legacy systems and really, just buy some stuff. It's like, is some other processor architecture going to come out of the woodwork? It's going to change everything? No, this is it. This is what you get. Intel does have their really, really dense CPUs coming in the first quarter of 2025, but those are the efficiency core based products. And they're probably going to be really good, but, there's always something better coming down the pike. And all these are really, really, really good right now. And this is basically all the cards on the table, except for that one that's coming in 2025. And AMD is going to sell every CPU that they make. Of that, I'm sure. I'm Bundle, this is Level 1. It's been fun hanging out with you for a little while. If you want to start your own thread, like the COMSOL thread in the forums, or you want to run some jobs, or help me understand your workload so that I can do better testing, let's hang out in the forums. Let's chat. Let's get you access to a system to play with and run some tests and see how it benchmarks. All right, I'm signing out. I'll see you there.
Acknowledge. Commander Riker will conduct a manual docking. The card out.
Sir.